Hey guys, I have your notes here for section 8.3, day 5, and we're going to be finding volume again today. So what we're going to start with is we're going to start with some type of shape on a two-dimensional piece of paper. We're going to maybe highlight the area that's bound between the curve and the x-axis or whatever. We're going to kind of highlight the two-dimensional area. We're not going to be revolving that area around anything. So we're not really like creating a circular object every single time. We're not doing that. We're going to take the area that we color, two-dimensional area that we color, and imagine building up from that. We're going to build a structure using our area that we color as like the foundation of a building. So what I'd like you to do is flip your paper over to example 2 on the back, kind of read through it, pause the video, read through it, and see if you understand it, and then I'll try to demonstrate it to you with a three-dimensional figure. All right, so hopefully you've done that. You might be clueless at this point, and that's okay. Let me explain what's going on in this problem. In this problem, we are starting with a circular base, and we're going to draw that circular base on a graph. So I have done that. I have drawn a circle with a radius of 1 centered at the origin on a graph. Now, on that circle, within that circle, we're going to build up from there. So picture this, the circle is like the foundation of a building that we're going to build. We're going to build up from there a bunch of different sized triangles, okay? And you can kind of see that these two triangles that I have built up from the blue circle, they're different sizes. Here's why they're different sizes. Each triangle stretches from one side of the circle to the other. So obviously, the triangle that follows the diameter of the circle is going to be my biggest triangle, right? Because a triangle from vertex to vertex, it touches the circle. That's going to be my biggest one. As I work my way across the circle, my triangles get smaller because from edge to edge of the circle gets smaller. Okay? And they've tried to draw this for you in this picture. So up here at the tip top is going to be the greatest triangle. They're equilateral triangles. And then as we move this direction, the triangles get smaller. See how you can see the triangles are getting smaller, triangles are getting smaller. If this were a building, the highest point would be in the very center of the building, which has the tallest triangle. Also, the edges of the building, think about this, the edges of the building over here, you'd have to like get on your knees to crawl in. Those triangles would be so small. So we're going to find volume of this three-dimensional building. I like to think of it as a building because we look at the foundation, like if we poured a concrete foundation and built up from there. I know nobody would make a building that looked like this, but our building consists of a whole bunch of super thin equilateral triangles, all different sizes. Our job is to take the area of each of those super thin triangles and add them all together. And when I add the area of each triangle multiplied by the thickness of the triangle, I'm going to get the volume of the object. It's called volumes of cross sections because once we take a three-dimensional object and we cut it at a certain point and we open it up and we look at what shape it's made out of, that's called a cross section. So volumes of cross sections. Now I'm going to start with the example 1 because it's actually an easier problem. All right, so we've got a function here. It's 2 sine x. So it's a normal sine curve except it goes up a little bit higher than your normal sine curve. It goes to 2 instead of 1. No big deal. And it's only half of the sine curve because it's going to stop us at, it says do only one arch. So it's going to stop us at pi because we're doing only one arch. Notice I've highlighted the area on the graph that we're going to be looking at. So what we're going to do is we're going to take that area, and from that area, now picture this line down, from that yellow area, we're going to build up from there some sort of shape. This is going to end up looking like a very oddly shaped building, and it's full of semicircles. So you can see that the largest semicircle would occur at the highest point, and then the semicircles get smaller as we approach either end point. And you can kind of see the drawing here. We're going to write a representation of the area of one semicircle. We're going to multiply that by its thickness, and then we're going to put it in an integral so that it calculates all of those areas and accumulates all of those areas. It's going to add them all together. All right, so area of one semicircle is going to be 1/2 pi r squared. Now let's look at what the radius is. So I've colored one semicircle, and in another semicircle I have put the radius here in blue. I've just highlighted the radius. Think about what that radius length looks like. It's a vertical measurement, and it doesn't go from the x-axis all the way to the function. It only goes halfway up the function. So my radius is half of the y value, because it goes from the 1/2 of the distance from the x-axis to the function. So my radius is 1/2 of the y value, and y is defined up there as y equals 2 sine x. So my radius ends up just being sine of x. Thus, my area is 1/2 times pi times my radius squared. That's the area, that's the representation of the area of one semicircle. Now, how thick are the semicircles? Well, see how they're all lined up here across the x-axis? These semicircles are super thin. And what do we call this along the x-axis? We're going to call that delta x or dx in an integral. So, here's what I've done. I've taken my area of one semicircle. I've put it in an integral. Now, I went ahead and put my constants out in the front. We're going from, this is where my semicircles start. This is where my semicircles stop. Notice these are x values. These are on my x-axis. This is my y in terms of x. So my radius squared. And then remember, this is the thickness of each circle. Now, if I just type it all in my calculator, I get approximately 2.467. That would be cubic units because we're finding volume. However, this does come out nicely. And watch. Let's say I leave this off. I do this last, okay? If I simply evaluate this integral, I do get an irrational number. But if I take the irrational number, of course, leaving off the pi right here, if I take this integral, which gave me an irrational number, divide the pi out of it, I get a nice fraction. I get 1/2. Now, put the pi back on it that you divided out on your calculator and include the pi over 2 that's being multiplied out front. And you actually get pi squared over 4 because this integral had a pi in it, and there's also a pi out here that you have to multiply. Okay? All right, moving on to the next one. So I have drawn like the area that we're trying to find here. The area that we're going to build up from. So this is the area where we're going to do our building, and in here we're going to create a whole bunch of equilateral triangles, just like I showed you here. Now we can position our triangles either way. We can build them up across the x-axis, triangle, 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 and we would accumulate them from x equals -1 to x equals +1. I think that's the way to go because most of you prefer being in terms of x. Since it's perfectly symmetrical, you could be weird, and some of you are. You could be weird and build up your triangles this way and go from y equals -1 to y equals +1, but I'll do the x one. So I'm going to draw one representative triangle. So an equilateral triangle, it's going to extend from one side of my circle to the other. This is the base of my triangle. And it's going to be built up from there, up and out. Well, I can't draw that very well, so I'm going to kind of lean it over. I'm going to take this triangle that I'm wanting to draw, and I'm going to kind of lean it over this way a little bit so you can see what it looks like. I think I did a pretty good job of trying to make it look equilateral. So, yeah. The length of the base is supposed to equal the length of each side. This is the base. So what I'm going to do is we need to work with this triangle because we got to do area of this triangle. 1/2 base times height. So I'm going to take this triangle and I'm going to redraw it two-dimensionally down here on my paper. I drew the triangle two-dimensionally. And you can see that all sides, I went ahead and marked all sides congruent. Now, let's investigate the base. Because my area is 1/2 base times height, what is my base? Let's investigate the base. What are you going to call a measurement that goes from here all the way to here? Some of you have it. Some of you don't. Let me ask it again. What do you call a measurement that goes from the x-axis all the way to your function plus the same thing in the other direction? So I think it's from here to here, I think it's Vy times 2. Which also means this is 2y and that's 2y. Now let's investigate the height. I need to draw the height coming down from the top vertex. I need to make it a 90-degree angle. Put an H there for height. Now it's kind of up to us to figure out what are we going to call that height. Well, keep in mind equilateral, so 60, 60, which means 30 up here. Okay, you remember your special right triangles? This, just look at the right triangle on the right side. So look from here over. This leg of this right triangle, from here to here, I call it the short leg. If the if the hypotenuse up here is 2y, the short leg is always half of that in a 30, 60, 90. So you can tell that this piece right here is just 1y, one of two ways. Hypotenuse is 2y, that's the short leg, that's half of it. Or you can say, look, when I knew this was 2y, and when I cut it in half, it's just y. And then the height, now the height is whatever the short leg is, multiplied by radical 3. So the height is y times radical 3. just like that. Now watch what happens when I take my area formula and I sub in what I know. Okay, so my area formula was 1/2 times the base, 2 times the y, times the height. Okay, not bad. Problem. Remember how up here I talked about you can do your triangles either way. We're going to do our triangles this way, right next to each other, right next to each other. We're going to start at x equals -1. We're going to do triangle after triangle after triangle after triangle all the way to x equals +1. So in my integral that I've created, these are x's. Right now, my area is in terms of y. So here's what we need to do. No problem. Go to the equation of your function. Go to the equation of your function and sub in whatever y is equal to. Just sub that in right here. Get this in terms of x. No problem. Go to your function and sub in what's our function? It's not given to us. You know it, though. I know you know it. Your function is a circle with radius of 1 centered at the origin. Oh no, it's not in y equals. Get it to y equals. Y'all are smart. You can do that. Y squared equals 1 minus x squared. Square root both sides. Now, technically when you square root both sides, you have to account for the positive and the negative root. However, since we're letting y represent a length, I think I'll just use the positive root. It really doesn't matter whether I'm using this y length, which is positive, or this y length, which is negative. It doesn't matter. Let's just use the positive one. So now, this is y. Sub that back in. Just like that. Okay, so I've got this right here is the area of, it represents the area of one triangle. It's a representation of the area of one triangle. So I'm going to put this in my integral from x equals -1 to x equals +1. We're going to multiply this by the thickness of each triangle. And then the integral is going to accumulate and add them all together. So I'm going to put my radical 3 out here, get that irrational constant out of the way. And if I go ahead and square my quantity, I can just write 1 minus x squared dx. That removes the radical. And just evaluating the integral, I got 4/3. So don't forget this that we put out in front. 4 radical 3 over 3 is the volume, and that would be cubic units. So remember, look at your two-dimensional area. You might want to take a highlighter or shade it with a pencil. Figure out what type of structure, what type of shape we're building up from there, and then work on the area of each of those individual shapes. All right, good luck.